Good morning, dear students. Welcome back to physics class. Today, I would like to teach you two main topics from thermodynamics, which are A. Isothermal and adiabatic process, and B. Second law of thermodynamics. In last class, you had studied the thermodynamic state variables and they describe equilibrium states of systems. And also you know that various state variables are not necessarily independent. The relation between the state variables is called the equation of state. Now I am going to discuss on very important thermodynamic process. They are isothermal process and adiabatic process. First, let's learn about isothermal process. Iso means same and thermal relates to temperature. In isothermal process, the temperature remains constant throughout while other variables change. You know the ideal gas equation, which is PV is equal to nu RT, where N be the number of moles of gas molecule which is constant, R be universal gas constant and T be a constant for isothermal process. This implies PV is equal to a constant. Here, pressure and volume are inversely proportional to each other. A process in which the temperature of the system is kept fixed throughout is called an isothermal process. If you draw a graph of pressure versus volume, you will get decreasing curve because both pressure and volume are inversely proportional to each other. Here, temperature is kept to be constant. This curve is known as isothermal curve. It is important to note that for an ideal gas, the equation of state is ideal gas relation, which is PV is equal to nu RT. For a fixed amount of gas, that is, it should have certain value of nu or number of moles. There are thus only two independent variables, say P and V or T and V. This pressure volume curve for a fixed temperature is called an isothermal curve. You have seen that the gas equation of an ideal gas, which is PV is equal to constant, was obtained when it considered the gas was in isothermal process. Here, the temperature T is kept constant. This equation shows pressure of a given mass of gas varies inversely with its volume. This is nothing but Boyle's law. Let us derive thermodynamic work done during the isothermal process. Suppose an ideal gas goes isothermally, which is at temperature T from its initial state P1 V1 to the final state P2 V2. Consider any intermediate stage where pressure is P and volume change from V to V plus delta V, where delta V be too small. Then what should be the work done? Work done, delta W is equal to P delta V. You know how it was derived in this form, which was learned from previous class. Taking delta V tends to 0 and summing the quantity delta W over the entire process. Then total work done W is equal to integration of P dV in the limit of V1 to V2. Don't forget this point. If you are going to take the summation of quantities of same nature in the limit or in certain range, you should take the integration operation. Here, range or limit is V1 to V2. Since very small quantity of work done, delta W is the product of the pressure P and very small change in volume delta V. We have W is equal to V1 to V2 integration of P dV. Since the ideal gas equation PV is equal to nu RT, so P is equal to nu RT by V. Then the expression becomes as W is equal to V1 to V2 integration of nu RT by V dV. As nu, R and T are constants, so they are taken out of integration symbol. So we get W is equal to nu RT V1 to V2 integration of dV by V. It is equal to nu RT integral logarithm of V2 by V1, which is the expression 1. Here we have to use the property of this integral operation, which is integration of 1 by V dV is equal to integral logarithm of V, and V1 to V2 integration of 1 by V dV is equal to integral logarithm of V2 minus integral logarithm of V1, which is equal to integral logarithm of V2 by V1. For 1 mole of an ideal gas, nu is equal to 1, then the work done W is equal to RT integral logarithm of V2 by V1, which is the expression 2. In an isothermal expansion, you know it is an isothermal process. There is no change in internal energy as there is no change in temperature. From first law of thermodynamics, which is delta Q is equal to delta U plus delta W, by putting the value of delta U, it is 0 as delta T is equal to 0, then delta Q is equal to delta W. This means the amount of heat energy supplied to the gas is equal to amount of work done by the gas on the surroundings. This is the form of equation of first law of thermodynamics in case of this isothermal process. What should be the nature of work done in both cases, isothermal expansion and isothermal contraction? You know that the expression of isothermal process for work done is W is equal to RT integral logarithm of V2 by V1. In isothermal expansion, the work is done by the gas, whereas in isothermal contraction, the work is done on the gas. Case 1. In isothermal expansion, final volume V2 is greater than initial volume V1. This implies W is greater than 0. Here, work done is positive, which means work is done by the gas, that is, heat energy is absorbed by the gas. And case 2 is, in isothermal contraction, V2 is lower than V1. This means that work done W is lower than 0. That is, work done is negative, which means that work is done on the gas, that is, heat energy is released. Let us see what is an adiabatic process. It is a process in which there is no heat flow take place between the system and the surroundings. Here, the walls of the container should be adiabatic. In an adiabatic process, the system is insulated from the surroundings, so the heat energy absorbed or released will be equal to 0. For example, let us consider hot tea in a thermoflask. It will remain hot as there is no exchange of heat energy because the walls of the thermoflask is insulated. We have the first law of thermodynamics. It is the general principle of conservation of energy, which indicates that work done by the gas results in decrease in its internal energy, and hence the temperature for the ideal gas. For an adiabatic process of an ideal gas, from Boyle's law, PV raised to gamma is equal to a constant, which is the expression 1, where gamma is the ratio of Cp to Cv. It is the ratio of molar specific heats at constant pressure and at constant volume respectively. If an ideal gas undergoes a change in its state adiabatically from the state P1V1 to the state P2V2, then the expression 1 becomes as P1V1 raised to gamma is equal to P2V2 raised to gamma, which is constant. It is the expression 2. The given figure shows the PV curves of an ideal gas for two adiabatic processes. One is expansion and second one is contraction, connecting two isothermal processes. Here we have plotted the graph by taking volume V along the x-axis and pressure P along the y-axis. Let us derive the work done in an adiabatic change of an ideal gas from the state P1 V1 T1 to the state P2 V2 T2. Here, work done W is equal to V1 to V2 integration of P dV. As PV raised to gamma is equal to constant, this implies P is equal to constant by V raised to gamma. Then W is equal to constant into V1 to V2 integration of dV by V raised to gamma, which is equal to constant into V1 to V2 integration of V raised to minus gamma dV. By applying the integration operation, we get work done W is equal to constant into V raised to minus gamma plus 1 by minus gamma plus 1. The limit is V1 to V2. So, W is equal to constant by 1 minus gamma into V2 raised to minus gamma plus 1 minus V1 raised to minus gamma plus 1, which is equal to constant by 1 minus gamma into 1 by V2 raised to gamma minus 1 minus 1 by V1 raised to gamma minus 1, since P1 V1 raised to gamma is equal to P2 V2 raised to gamma, which is constant. Then W is equal to 1 by 1 minus gamma into P2 V2 raised to gamma by V2 raised to gamma minus 1 minus P1 V1 raised to gamma by V1 raised to gamma minus 1. Here we have substituted the constant values. First one P2 V2 raised to gamma and second one P1 V1 raised to gamma in the corresponding part of the above expression. It is equal to 1 by 1 minus gamma into P2 V2 raised to gamma by V2 raised to gamma minus 1 minus P1 V1 raised to gamma by V1 raised to gamma minus 1 is equal to 1 by 1 minus gamma into P2 V2 minus P1 V1. Here V2 raised to gamma by V2 raised to gamma minus 1 is equal to V2 and V1 raised to gamma by V1 raised to gamma minus 1 is equal to V1. So we have got the expression in this form: W is equal to 1 by 1 minus gamma into P2 V2 minus P1 V1. As PV is equal to nu RT, then P1 V1 is equal to nu RT1 and P2 V2 is equal to nu RT2. By solving, work done W is equal to nu R by 1 minus gamma into T2 minus T1, or W is equal to nu R by gamma minus 1 into T1 minus T2, which is the expression 3. We have the thermodynamic work done in adiabatic process. W is equal to nu R by gamma minus 1 into T1 minus T2. If work is done by the gas in an adiabatic process, here W is greater than 0. From the expression, it is seen that T2 is lower than T1. On other hand, if work is done on the gas, here W is lower than 0, then we get T2 is greater than T1. That is, the temperature of the gas rises. It is important to note that if work is done by a gas, then W is greater than 0. It means W will be positive. And if work is done on the gas, W will be lower than 0. Then W will be negative. Now I am going to introduce second law of thermodynamics. Can you imagine the thermodynamic process such as the transfer of heat energy goes from a cold object to a hot object, if it conserves energy or not? Definitely, it will conserve energy, but which never occur naturally. For example, if we bring a hot object into contact with a cold object, we observe that the hot object cools down and the cold object heats up until an equilibrium is reached. The transfer of heat energy goes from the hot object to the cold object. Now, you can imagine a system, however, in which the heat energy is transferred from the cold object to the hot object. Such a system does not violate the first law of thermodynamics. The cold object gets colder and the hot objects get hotter, but energy will be conserved. Clearly, we do not encounter such a system in nature, but there are devices in which such thermodynamic process can take place. Example, refrigerator. To explain this and similar observations or process, thermodynamists proposed the second law of thermodynamics. There are two statements of second law of thermodynamics given by scientists. First one is Kelvin-Planck statement and second one is Clausius statement. What is Kelvin-Planck statement? No process is possible whose result is the absorption of heat energy from a reservoir and the complete conversion of the heat into work. And Clausius statement is no process is possible whose result is the transfer of heat energy from a colder object to a hotter object. Now you have to see the explanations given by the statements. First one is Kelvin-Planck statement. It is always impossible that the total amount of heat energy which is supplied to a system will get converted into work, and there will be loss of heat energy. So, complete conversion of heat into work is not possible. And second one's explanation is transfer of heat energy from a colder body to a hotter body will never take place until some external work is done on the system. For this external work, we have to use some techniques in working of this kind of devices. Example is working of the refrigerator. Dear students, today's homework questions are given in this slide. Please, you have to work out these question answers by today itself. Okay, thank you. Have a nice day.